So you have the ground state, first region, second region, third region. Okay, the first region exponential decay this way, third region exponential decay that way. In the middle, it's an even function, cosine kx. I still have three coefficients, a, b, c, that I have to figure out, along with kappa and k. And don't forget, the kappa and k both depend on E. There is an energy expression. So in general, we have 6 unknowns, A, B, C, K, kappa, and E. Now, if E is an arbitrary energy, which means any energy will do, then you will not have an equation which will fix what E is, right? Which means E can be anything, therefore there will be what? No quantization of energy. Is that true? If we had enough number of equations to fix A, B, C, K, kappa, and E, that would tell us that E, you cannot just choose anything. It has to satisfy these equations. So then E would assume only certain allowed values, and therefore we say it must be quantized, right? Let's see if that's the case. Again, I have 6 unknowns, A, B, C, K, kappa, E. How many equations do we have? Well, we have, first of all, we have the normalization condition. That's one of them. Okay, the total chance of finding the particle everywhere in space must be 0. I'm sorry, it must be 1. Okay, and also, what about k squared plus kappa squared? Now, you recall the definitions of k and kappa here. This is a k squared without negative sign, okay? This is kappa squared. And if you add them together, you find the negative e and positive e, that cancel out, and you're left with a constant. What is that constant? What is that constant? You just add them together. 2m u naught over h bar squared. M is the mass of the particle, u naught is the height of the potential barrier. These are constants. So k squared plus kappa squared is in fact a constant. Well, I have 2 equations already, but I have 6 unknowns. So do we have 4 more equations? If I can actually come up with 4 more equations, then I would say I have a total of 6 equations. I can fix all of these things. That tells me E, the energy, is not arbitrary. It must depend on those parameters like m, like u naught, like h bar, and so on, which means energy is quantized. You cannot just throw any energy into this particle and expect to live there. It must satisfy certain specific conditions. Okay, so do we have 4 more equations? And the answer is yes, we do. What 4 equations can we come up with? Well, remember, the continuity of the potential of the wave function when it crosses between different regions. Here you have region 1 and 2. Here you have region 2 and 3. Now, U is not infinity, unlike the previous case. Okay, U is not infinity. U naught is not infinity. Therefore, not only is psi continuous going from here to there, so is the first derivative deep psi dt. I'm sorry, deep psi dx. So there are 2 continuity conditions on this border going from here to there. That is continuity of psi and deep psi dx. Same thing happens here. As you cross from region 2 to 3, you have 2 more continuity equations you must satisfy. One is psi has to be continuous. The other is deep psi over dx must also be continuous. So indeed, we have 4 more additional equations. So in theory, we have 6 equations and 6 unknowns. Everything, including the energy E, must be fixed. You cannot put any value of energy in there. So you can expect energy to be a set of discrete values only, not arbitrary values. That in fact explains the idea of quantization of energy in this case. But what is the energy equal to? And what is the corresponding wave function for each eigenstate? Well, let's see. I am interested in E. That is the primary thing I'm interested in. I already know the wave function. Those A's and B's and C's, I mean, it's nice to find them out, but I don't really care that much. I mean, these are just coefficients in front of that. Is there a way for us to bypass any knowledge of A, B, C, and go directly to the energy E? Well, it turns out, yes, I can do that. Okay, take a look. There's a small trick that we can use. At x equals negative L over 2, which is the left edge here, negative L over 2, left edge of the potential well, I have the continuity of these 2 wave functions as well as the continuity of the first derivative. Now, the wave function here has to do A, here has to do with B, right? and you have A here and B here. Remember, I don't want to know A's and B's. I just care about the energy. Can I get rid of those A's and B's? Yes, it turns out we can do that, because if I divided this by that, then this has A here, this also has A here, this has B here, this also has B here, so that would cancel, right? Now, what if you actually did that? You divided the first derivative by the function itself, then don't you get this, right? This, and this division equals that division, so therefore you get this equals that. But take a closer look. What is d phi over dx divided by phi itself? Isn't that d dx of the natural log of this thing? Because we know d dx natural log y equals 1 over y dy dx. Isn't that true? Right? And then this y is outside here, and therefore this is the same as that. So what does that tell us? It tells us that instead of saying psi is continuous and deep psi dx is continuous, we can say the derivative of the natural log of the wave function must be continuous at the border. What is the advantage of this over those two? Because when you take natural log, you'll find that those coefficients a and b and c, they will just drop out. They do not appear anymore. That is the nice thing about it. Otherwise, you can just solve for those two and just find a, b, and everything else, even though we don't really care. Okay, that is the little trick I'm talking about. Okay, instead of dealing with the wave function itself, I deal with the natural log of the wave function. It has to be continuous. Now, similarly, at x equals a positive L over 2, that's the right edge of the potential area, I have, again, the natural log of the wave function going from region number 2 to region number 3 must also be continuous, right? And let me plug in some numbers, okay, for this one and for this one. Now, for the first one, at the left edge, this side is psi 1, so psi 1 is, remember, e to the kappa x, and that side is psi 2. Psi 2 goes into the inside the well, so it's a cosine function, right? So I have this, that is x equals negative L over 2. And that one is on the right edge when x equals positive L over 2. You go from the cosine function in region number 2 into the exponential function in region number 3. Now, all you have to do now is to finish this differentiation. For example, this is just, what is this? Natural log e to the kappa x. It's just kappa x. So this is just kappa. This side is just kappa. And that side, natural log of cosine x derivative. You move cosine x down first, and you cosine x take derivative again, because then you get negative sine kx, right? And the sine over cosine, that's tangent. So you have kappa on one side and tangent on the other side. That is what you do when you finish this derivative. And what if you do that for the other side of the potential well? It turns out that you just get two identical equations, okay? It doesn't matter whether you did it here or there. That's nice. So that's the equation we come up with. You work on either one of them, you get the same thing, okay? They do not conflict with each other, thank God. So you get k times tangent of kl over 2 equals kappa. But remember, k and kappa satisfy another equation right here. That's due to the definition k and kappa, right? K is defined as this, kappa is defined as that, so therefore the sum of the squared equals a constant. So now I have two equations for k and kappa. Here's the first equation, boundary conditions. Here's the second equation due to the definition, k and kappa. And I would have set out to solve this pair of equations for k and kappa. I get either one of them, I can find the energy E. Okay? So how do I solve these equations? At this point, let me introduce what's called a dimensionless number. KL over 2 must be a dimensionless number because it's an argument of a tangent function. It's an angle. Let's call that psi. Let's call this psi. And let me also introduce a similar dimensional number called eta. Eta is defined as kappa L over 2, not KL over 2. So these are both dimensionless numbers. Introducing these two dimensionless numbers, we can replace k and kappa, which are dimensional numbers. So this pair of equation now become that pair of equation. Right? You see, for example, psi replaces KL over 2. That's our definition. And here you have, instead of k squared plus psi kappa squared, you have psi squared plus eta squared, and so on. So this is the pair of equations we must solve. When we solve psi and eta, we can find k and kappa, and from which we can find the energy. Now, take a good look at these equations. Can we really solve them easily? The second one looks very innocent. It's just psi squared plus eta squared equals a constant, which means when you plot psi and eta, this second one will just give you a circle, right? It'll give you a circle. So the solution must be somewhere on the circle. But the solution must also satisfy the first equation. And that is where things get touchy. Because this first equation is nothing ordinary. It's not a power function of anything. Okay? This is, again, an example of what's called transcendental equation. And we cannot solve it with analytical solutions, unfortunately. But that's okay. What we can at least do is to solve it graphically. What do I mean by that? What I mean is when I plot psi and eta, or eta and psi, I will get two curves, right? The second curve is a circle. The first curve you'll see in a minute what it looks like. And when these two curves cross each other, I found a solution because it satisfies both of these equations. That would be my solution. So here is a plot of eta and psi. The green circle represents our second equation, okay? Eta squared plus psi squared equals this constant, mu L squared over 2h bar. And the red curve represents our first equation, which says eta equals psi tangent psi. Now take a good look to see that actually makes quantitative sense. When eta equals 0, psi is also equal to 0. Start from 0. Okay? And then as psi increases, so does eta. So it goes up, goes up, goes up. But when psi goes to 90 degrees, or pi over 2, tangent psi goes to infinity, and therefore eta has to go to infinity as well. So it shoots all the way to infinity as psi goes to pi over 2. Okay? And this is not the only curve I can find for that. There is another segment starting from pi when tangent pi is 0, so psi is 0. Eta is 0 when psi equals pi, so you start from here. It also goes up when psi becomes 270 degrees, or 3 pi over 2. Again, tangent psi goes to infinity, so eta shoots to infinity. So you got a whole bunch of branches. 1, 2, 3, 4, and so on for the second equation. It's a multi-branch curve. Now, the first equation, the green circle, it's just a circle. It's only one circle. But as I increase the depth of the potential well, U0, what happens to the radius of that circle? The radius increases, right? So let's imagine we start from a small circle. Okay, small circle, small radius, which means the depth of the potential well is shallow. And then it's so shallow that the circle is very small. It never crosses the second branch, let alone the third branch or the fourth branch of that equation. But it can certainly cross the first one, right? Because the first one starts from 0. So you have at least one solution. Okay? That solution corresponds to lowest energy. That is the solution corresponding to our ground state. So there is always a ground state, no matter how shallow that U0 is. Now, as U increases, the size of this green circle will increase. At some point, it will be large enough so that it actually crosses not only the first branch, it actually crosses the second branch as well. Okay, so let me draw a circle like this. It's a bigger circle. This circle is big enough so that it starts to touch the second branch. All right? Now this circle actually crosses the red curve twice. One is here, one is there. This one is the ground state. Here is our second solution. Again, this is an even parity case. Okay, I only consider the even parity case. Even parity case, how come we have two solutions? This is the ground state. What do you think that one is? That one is the next even function, right? Is it the first excited state? No, because it alternates between even and odd, right? So the ground state is even. The first excited is odd. We don't even use that curve. The second excited state is the next lowest even one. So this would be the second excited state. When U is large enough, you will have two even functions that are trapped inside this potential well. Here's one. Here's one. Here's the next one. But if the well is shallow enough, you would only have one ground state for even, and that's it. There's no such second crossing. But imagine when U is really large, okay, you know, it's that large, it can cross the first one, second one, third one, then you will start to have more and more eigenstates that are even. So you have more, basically you can trap more possible energy values. And again, following our general discussion about parity, we would have the ground state being even. That's when anchored 1. First excited state, second excited, third excited state. This is the ground state. This one is the second excited state, which is our next even parity one, and so on. I did not find a solution from scratch for the odd parity, but if you did that, you can actually just go back and try it for yourself. You can just go back to this page, all right? And oops, that's not, yeah. You just go back to this page. Instead of the ground state, you say, I'm going to now look at odd parity case, not even. This is still the same. This is what you have to do is to change what? Change this. Okay, this is no longer cosine kx. It must be sine kx, right? Because it's odd. And then, you know, this definition is still the same. This idea is still the same, but the answer will be a little bit different. You will have one equation the same. That's the just how you add kappa squared and k squared. That never changes. But the second equation is no longer this, but rather becomes that. It becomes eta equals negative psi times cotangent psi. This guy starts out from pi over 2 as 0, because when psi equals pi over 2, you have cotangent of pi over 2. That's 0. So start from 0 here, not there. Okay, and it goes up to infinity when psi equals pi, because cotangent pi goes to infinity. So it's like this. This red curve no longer starts from the origin. Now, the green circle still starts from the origin. And you see here, now we have a problem. The problem is, unless this green circle has big enough radius, it will never actually meet this red curve even once. You know what that means? There will be no solution to even one odd parity wave function, which means even the first excited state will not exist. Okay? You only have a ground state. That's it. That is guaranteed. But as this green circle gets bigger and bigger, let's say it gets that big, because the potential gets deeper, you will have a solution. That is your first excited state, which corresponds to this. The first excited state, odd function, odd parity. Okay, so in general, we learned that you can trap a certain number of bound states inside a potential well, but how many can you trap actually depends on how deep that well is. The deeper the well, the more states you can get. No matter how shallow it is, you are always guaranteed one solution, the ground state, which is even with no nodes. But whether you're going to have a first excited state, the second excited state, or even a third excited state, and so on, that is not guaranteed. That would depend on how deep that well is. And for the first excited state to ever exist, the radius of this psi squared plus eta squared must be at least equal to what? Pi over 2. Okay? Then you have, you know, one cross point, barely able to make it. And what is the condition for the second excited state to exist, which is this one? That means psi squared plus eta squared must be greater than pi over 2. In fact, it must be equal to pi. Okay? Must be equal to pi. That's when you cross. That's when the line crosses the second branch, just barely, and so on. Now, to summarize what we discovered, let's write it here again. There is always a ground state, no matter what. The first excited state, the lowest, which is the lowest odd parity state, that is this guy, right? That is this guy. So that tells us that eta squared plus psi squared must be, which is, okay, that tells us that eta squared plus psi squared, which is equal to mu naught L squared over 2h bar squared, must be equal to at least this radius squared. Now I shouldn't have said pi over 2, I should have said pi over 2 squared. Okay, this is radius squared. So that would be at least pi over 2 squared. Okay, this in fact is the, well, I'm sorry, I screwed up. The first excited state, that's an odd parity. I have to look at this curve. Okay, for this curve. For this curve, the first excited state, the circle has to grow at least to this size, right? At least to this size, and this is pi over 2, okay? This is pi over 2. So I should be using this curve. The answer is the same, but I have to use this curve for odd parity. So the eta squared plus psi squared must be greater or equal to at least pi over 2 squared. From here, you can solve for u naught. U naught has a minimum value. Below that value, the first excited state will not exist. You will only have a ground state. Now, what about the second excited state? Here is the second excited state, once again, of even parity. Psi squared plus eta squared, in this case, is equal to radius squared. That radius must be at least equal to pi. So therefore, psi squared plus eta squared, in this case, must be equal or greater than pi squared. Okay, not half a pi squared. So I have an even stronger condition, eta squared plus psi squared, which is equal to m u naught L squared over 2h bar squared must be greater or equal to pi squared. If u naught satisfies this, you're going to have not only the ground state and first excited state, you're also going to have a second excited state, and so on. Now, if you had a solution to this equation, you would know what k is, what kappa is. And given k and kappa, you would know the wave function, because here is just, e to the positive, negative kappa x outside. Inside is either sine kx or cosine kx. So from that, you can do some plot of the wave functions. Here is your ground state. Again, there is no node. Okay, there is no node, and it's even. Here's the first excited state. There is one node in the middle. It's odd. Here's the second excited state. There are two nodes, and it's even, just like we suspected before. These wave functions look kind of like the wave function for infinite square well, except for the case of infinite square well, u is infinity here and there is no leak of the wave function outside. It should go abruptly to 0 here and 0 here. Otherwise, it looks kind of similar. And here is psi squared. Psi squared represents what? The probability density of finding the particle. So here, the probability density is 0, so the particle can never be found here and there, but it's more likely to be found here, here, and here, and so on. That's for the second excited state. For the ground state, it's more likely to be found here, most likely to be found here, and there is also a likelihood it can be found somewhere outside the classically allowed region into classically forbidden region, even though the chance of penetrating deep gets smaller and smaller and smaller exponentially. And we have done the case of both the infinite square well and finite square well. But we know that if we take u naught to infinity, we should go back from the finite square well to the infinite square well, right? For the finite square well, the solution, as you know, is graphical. It's not easy to do, even though we can find it graphically. But for the infinite square well, there is a very simple solution, analytical solution. So how does that, do they agree with each other? If we take u naught equal to infinity, then by definition, the radius of our first circle, sine squared plus eta squared, here's the radius squared. That radius squared goes to infinity, right? When the radius squared goes to infinity, let's take a look at these curves again. These plots of eta and psi. Here, the circle has infinite radius for both the even and odd case because they're both proportional to u naught, the radius. And what that tells us is that the green circles, being infinitely large, must meet up with the red curves at where? At those points, right? Only at those points, those points. Because that's where this red curve also extends to infinity. They have to meet at infinity, remember? But this is where psi equal to pi over 2, pi, 3 pi over 2. And this is where psi equal to pi, 2 pi, 3 pi, and so on. So in general, whether it's even or odd, we found that psi must be n times pi over 2. If n is even number, we get this case. If n is an odd number, we get that case. So we go back to here. Psi must be a multiple of pi over 2. That is the solution. But psi itself is equal to kl over 2 by our definitions. Therefore, k is 2 psi over l, psi being n pi over 2. So you see k equals n pi over l. That's exactly what we got before. This is from the boundary condition that k times l must be equal to 0, must be equal to n pi at the border to ensure that sine kx goes to 0 there. So you see, we do go back to the infinite square wave case. All right, so before we close our discussion on the finite square wave, let's ask ourselves this question. We saw that energy was quantized in this case, right? Energy was quantized, just like the infinite square wave. But we ask ourselves this question: why is the energy quantized? Why is it energy can only be E1, E2, E3, and so on? Well, it's because we had plenty of equations to fix everything, including the energy. And these equations, where do they come from? Well, you have the definition K and kappa. That's just the definition. You have the normalization condition, which is just normalization condition. But where do the other four equations come from? They come from the boundary condition at both two ends of the potential wave, x equals plus or minus L over 2. So you see, the reason why energy is conserved is because the solution to the Schrödinger's equation must satisfy the boundary conditions. Here in this case, there are actually four borders, x equal to plus or minus infinity, and x equal to plus or minus L over 2. When you have to satisfy all these boundary conditions, you find that energy would have no choice but to be a series of discrete values, otherwise you will break these boundary conditions. So the quantization of energy in both cases of infinite and finite square wave, the condition of quantization of energy is not artificially imposed, like what Planck did, artificially imposed without any reason. There is a good reason why energy is quantized. It's because the wave function must satisfy the boundary conditions. That leaves you with no arbitrary possible value of energy, but only discrete set of values. So, let me ask you this question. You call this course quantum mechanics or quantum physics. Does that mean energy is always quantized, or everything is quantized in quantum mechanics? Is quantization of energy a first principle in quantum mechanics? First principle means we cannot derive from anywhere else. The answer clearly is no. First of all, energy is not always quantized, even in quantum physics. And secondly, energy quantization, when it is quantized, is not an arbitrary condition with no reason. The quantization of energy is a requirement from satisfying Schrödinger's equation for the boundary conditions. And the fact that you can use the Schrödinger's equation to solve for the problem is because you can describe the particle as a wave. So the wave-particle duality is at the source of it all, not the quantization of energy. The quantization of energy is actually a result of using a wave to describe a particle. It is a result of the wave-particle duality.